Okay, well, I hope everybody's having a good day. We're going to continue talking about the graphs of sine and cosine, and we're going to start getting into the transformations. But a few things. The quiz I had scheduled for today, I'm going to go ahead and move it to Monday. Because of the pep rally happening during 8th period, I'm going to lose probably 90% of that class. So I figure it's just better just move it to next week. Have everybody take it all at the same time. So that'll give you a little more time to prepare. I did not put the ambiguous case side-side angle on the quiz. It's very similar to your homework. You'll have a couple of word problems, but the test coming up in just under 2 weeks on the 21st, that will definitely have the ambiguous case on there. So you want to be familiar with that. This is one of the last classes I can say this to because waivers are due by noon today to Mr. Young's office. So if that applies to anybody, if you happen to have failed the second 6 weeks where you have an upper level or class and you belong to an extracurricular activity, something of that sort, okay, that is available for you, but time is very short. All right, let's go ahead and talk about sine. So we spent quite a bit of time yesterday talking about why sine looks the way it does and comparing it to the unit circle, but I also really wanted to go ahead and emphasize some key points that we are going to look at. Now, sine, did it begin with a maximum, a zero, or a minimum? Okay, 0. Okay, and then we go to maximum, then a 0, then a minimum, and then we finish up with a 0 again. So sine, one period, one cycle looks like this. Okay, now why is the period of sine 2 pi radians? Okay, what's that, Will?
Pi radians is equal to 1 revolution.
There you go. For every one revolution around the unit circle, one revolution is this one cycle of the graph. Okay, so as you continue to rotate, the graph is just going to continue to repeat itself over and over again. Now, we went ahead and listed these values verbally and the other day. So we went ahead and said, you know, maximum, 0, all that good stuff. But now we're going to go ahead and list them as the numerical values. So we're going to go ahead and say 0, the maximum is 1, 0, minimum's -1, and then we have a 0. Because we're going to get into the transformations today, and any vertical transformations are going to go ahead and apply to these directly. All right, so those are going to be coming up in just a few short minutes. Now, any questions about sine itself or about any of the characteristics that we were looking at yesterday? Okay. All right, well, let's move on to cosine. Let's do the same thing. But cosine did not start with a 0. It started with what? He started with a maximum. And then he went to a 0, then a minimum, another 0, and we have a maximum at 2 pi. So cosine is going to look like this curvy V. This is the section that repeats over and over again. And it has a period of 2 pi for the same reason that sine does. Okay, one revolution is going to give me this one section of the graph. So the more I rotate, the more it's going to repeat, whether it's counterclockwise or clockwise. So we're going to use the same values. Maximum 1, then we have a 0, minimum -1, 0, and then we finish up with a maximum again. Okay, so just like before, any questions on the graph, why we have the points that we do, anything about the characteristics anybody would like to discuss, maybe a little confusing or you're not quite sure about? Okay, if you do have any, let me know. Let's go ahead, push forward into our transformations. So these are going to be broken up into different topics today, but it's the same transformations that you started to learn in Algebra 2. It's the same ones that we've learned in here at the beginning of the school year with our review material. We're talking about dilations, reflections, and shifts. Okay. So this first one is amplitude. We can change the height or amplitude of the graphs of sine and cosine functions by transforming the equation of the function. This will change the range of the parent function. Okay, so let's just go ahead and get right into it. I want to graph y equals 2 sine of x. Now for each of these, I want to go ahead and hopefully tie it back to the way you were instructed in Algebra 2. I want to graph the parent, what we're going to call the pre-image first, with a dashed curve. And then our final transformation, we're going to go ahead and draw with a solid curve. We call that the image. Do those vocabulary words sound familiar? Okay, the pre-image is the parent before the transformations. The image is the final transformation. Okay, so right now we're not going to start with 2 sine of x. Let's just graph sine of x. Remember, sine started with a what? Max, min, or 0? 0. Then went to a max, then a 0, then a min, and then a 0. So this is going to be the graph of sine of x. Okay. Now, what kind of transformation do we see here? Is that a reflection, is that a shift, or is that a dilation? It is a dilation. Now, you can always tell by the operation. If you're multiplying, it's going to be a dilation. That means the graph is horizontally and vertically expanding or compressing, shrinking, or stretching. If you're going to be working with a shift, remember you're going to be adding or subtracting values. And then, of course, a reflection is what? A negative. There you go. The negative's one job is to reflect. Now, is this happening vertically or horizontally? It's not horizontally. How do we know? There you go. It's only a horizontal transformation if it is directly affecting x. With these problems, typically you're going to see parentheses around the x. So anything done in the parentheses, a good rule of thumb, is going to happen horizontally. Anything outside the parentheses is going to be vertical. Now, since this one doesn't have parentheses at all, yeah, we're just multiplying the trig function by 2. Yeah, this is a vertical, what though? Expansion or compression? Yeah, expansion. So nothing is happening horizontally here. So all I want to do is focus on the y values of those key points. Remember those that I just listed. Okay, we started with a 0. We had 1, 0, -1, and then a 0. So any vertical transformations are going to apply to these key values. So all we're going to do here is just multiply each of them by 2. Okay, but the good news is, what's 2 times 0? 0. So all of these points are going to seem to be anchored right where they are. They're going to stay in the same place. So 2 times 1 would give me 2, while 2 times -1 would give me -2. So we should have something like this. This is going to be 2 sine of x. There we go. And what we would expect to happen is exactly what we see. The graph was expanded vertically by a factor of 2. So this does change one of the components. The domain is still all reals. He's infinitely wide. But the range is now what? There you go. See, he's bounded above and below by -2 and +2. Okay. So we're just going to start off with some real basic transformations, and then we're going to build towards some more complicated ones. Okay. Does anybody have any questions on that? Anybody having a hard time? Okay. All right, well, let's try this next one. Graph y equals -2 cosine x. So let's start with the pre-image. Again, that's the parent. Cosine starts with what? A maximum. Then we have a 0, minimum, 0, maximum at these key locations. 0, pi over 2, pi, 3 pi over 2, and 2 pi. So it's going to look something like this. Okay, there's cosine of x. Okay. Now, how many transformations are happening here? There are actually 2. We don't want to look at that scale factor as a -2. Look at it as a negative and a 2. The negative is going to reflect it, but now it's going to reflect it with the x or the y-axis. Okay, so I've heard some x's and I've heard some y's. It is the x-axis. If the function itself is negative, it's going to reflect it with the x-axis. So where would the negative have to be if I wanted to reflect it with the y-axis? Presumption? Inside the parentheses, x itself would have to be negative. That's exactly right. Okay, so the negative is going to reflect it, so we still have the same scale factor. Okay, 2. So this is also going to result in a vertical expansion. So it's going to stretch it, and it's going to go ahead and reflect it. Now, because both of these are happening vertically, again, we're just going to apply them to these key values, the y values from those 5 points. So each of these we're going to multiply by -2. So it's going to give me 0. Okay. Then we're going to have what? Oh, what am I talking about? I'm sorry. I was thinking that, yeah, that's sine. I'm sorry. Our key values for cosine, we switched functions. This is 1, 0, negative 1, 0, 1. Pardon me. We're going to multiply each of these by negative 2. So this is negative 2, 0, positive 2, 0, and another negative 2. Okay. So we have negative 2, because nothing is happening horizontally, so these points are remaining on the same vertical lines that they have now. This is still going to be at 0. This one right here is now at 2. This one's at 0, and this last one's at negative 2. There we go. And this right here is negative 2 cosine of x. All right, and it was reflected. Okay, and it was vertically expanded by a factor of 2. There you go. So that's the good news about these next upcoming lessons. It's the same transformations that we've been looking at for quite a while, even before you met me. We're just now applying them to new graphs. Okay. Now, let's go ahead and fill in the bottom down here. It says in both examples, the amplitude is what? What do you think the amplitude is of both of these graphs? Okay. No, the actual amplitude, not the formula. What's the leading scale factor? 2. Again, doesn't matter if it's negative. Okay, remember we just talked about the scale factor, we're looking at it as a separate value from the negative because they're two different transformations. Okay, so basically when we're talking about amplitude, we're referring to half the height of the wave. In general, we can say that if y equals a sine of bx, or if y equals a cosine of bx, then the amplitude is defined to be the absolute value of a. So on problems where you're asked to find the amplitude, it's the absolute value of that leading scale factor. Okay, what we're going to refer to as a. Now it says when the value of a is less than 0, describe the behavior of the graph's key points. Well, we already talked about the reflection. Those key points are going to be reversed. Okay, so now what I want to go ahead and do today is I'm going to introduce you to a new graphing strategy. Typically what I've done in the past is I go ahead and take points just off the parent, and then I go ahead and apply the transformations, horizontally to the x's, vertically to the y's, and then I plot enough points so that I can see what the transform function is. But over the past year, I've been working a lot closer with Mr. Heinrich, because from here, you guys are going to him. So we want to make sure that we're staying consistent. So I'm going to show you another method. All right. So here's the thing. Let's talk about period. We've already established that the period of a parent sine or cosine graph is 2 pi based on the number of revolutions. Okay. Let's explore how the general form of the equations can change the period of the graph as well. Now, you remember what I said about inside and outside the parentheses? This is a perfect example. Okay. We don't have anything happening outside the parentheses, so there are no vertical transformations as in the previous graphs. So those key values, the 1s, the 0s, the negative 1s, they're staying the same. But because I have something directly applied to x, this is going to change horizontally. So is this a dilation, a shift, or a reflection? It is a dilation. We're multiplying. So can anybody tell me what happens? Because remember, with the x's, it gets a little trickier. What happens when I multiply x by a value, in this case 2? Okay, what's that, presumption? You take the reciprocal of it? Okay, so what does that mean for the graph? What's going to happen? It is going to dilate. So would this result in a horizontal stretch or a shrink? Okay, why a shrink though? It says 2. You said we'd have to take the what? That's right. Whatever you're multiplying x by, the true scale factor is the reciprocal. Okay? Because the reciprocal is smaller than the original value, this is going to result in a horizontal compression. Okay, so it's only going to take me half as long for this graph to repeat. So we can already go ahead and kind of predict this. If the original graph has a period of 2 pi, and I'm going to shrink it by half, well, what should the period be now? 1/2 pi?
Or just pi.
Just pi. There we go. Now here's how we're going to go ahead and start the strategy. You're going to take whatever horizontal transformations are inside the parentheses, and you're going to go ahead and put it between a lower and an upper boundary. So I'm going to go ahead and take 2x, and I'm going to put it between 0 and 2 pi. Now whether you're graphing sine or cosine, you're always going to go ahead and do this. Whatever horizontal transformations are taking place, you're going to put it between 0 and 2 pi. The reason being, the parents have an original period of 2 pi radians. Okay. Well, what I want to go ahead and do now is simplify this. We're just going to treat it as a compound inequality because that's what it is. How would I get x isolated in the middle? Yeah, just divide by 2. But I've got 3 parts here. So if I divide the middle by 2, I'm going to divide the left, and I'm going to divide the right. So 0 divided by 2 is 0. Less than or equal to x, which is less than or equal to pi. And remember, what did we say a second ago? If this graph is going to repeat in half as many radians as it did originally, then its period would be pi. This is telling me what the period of the transformed graph is going to be. All right. So now here's the thing. I've got that set up, so now I'm going to turn my attention to the vertical transformations. But what did we say about this? What are the vertical transformations here? Nothing's happening vertically. So those key values are remaining the same. Now, since we're dealing with sine, remember he starts with a 0, then goes to a maximum, 0, minimum, and then back to a 0 again, right? So what I'm now going to do, I'm going to take the lower boundary of my simplified compound inequality, and I'm going to pair it with the first y value. Then I'm going to take the upper boundary, and I'm going to pair it with the last critical value. Okay, right there. What I'm doing is I'm creating ordered pairs for one full period of the transformed graph. Okay, is everybody with me? Now, here's the thing. We need to go ahead and figure out what these missing values are going to be, these x's, for these y values down here. So there's only 2 things you need to do. First, take your upper boundary and subtract your lower boundary. What's pi minus 0? Pi. Now, whatever that distance is between the upper and the lower boundaries, you're always going to divide by 4. Okay. That's the value that I need to add over and over as I start with 0. Okay. Now, does anybody want me to elaborate on kind of why I need to divide by 4? Okay. Let's go back to the original graph. And it doesn't matter if it's sine or cosine. Okay. Let's say we're looking at the graph of sine right here. Well, we've been focused on these 5 key points, right? So here's 1, 2, 3, 4, 5. Okay. Well, if I'm looking at those 5 themselves, there are 4 horizontal distances between each of them. Here's 1, here's 2, here's 3, here's 4. Each of those distances is going to be the exact same length. That's why we always divide by 4. Okay. So now coming back over here to our problem. All right. What is 0 plus pi over 4? So that's pi over 4. See, whatever value you find, the difference of your upper and lower divided by 4, you're just going to add that over and over again until you completely fill in the top row. So now what's pi over 4 plus pi over 4? Okay, that is 2 pi over 4, which is pi over 2. Now what's pi over 2 plus pi over 4? Okay, that is 3 pi over 4. Now, if you've done it correctly, if you've got the right value, you should be able to add one more time, and it's always going to give you your upper boundary. So what is 3 pi over 4 plus pi over 4? It is pi, 4 pi over 4. But see what I've done here, these are my x's, and these are my y values. So I've given myself 5 ordered pairs that exist on sine of 2x. So this one right here is 0, 0. The next ordered pair would be pi over 4, 1. And then you would just go straight down the line. Okay. Now, let me go ahead and draw the pre-image, and then I'll go ahead and draw the image. We're drawing sine, so this is a 0, max, 0, min, 0. Get a little more in there. So that is sine of x. Okay. Now, let's go ahead and plot these ordered pairs. We have 0, 0. Where's pi over 4? Yeah, it's going to be halfway between 0 and pi over 2, right? So pi over 4, 1. Then we have pi over 2, 0. 3 pi over 4, negative 1. That's going to be halfway between pi over 2 and pi. And what's our last ordered pair? Pi comma 0. And you'll notice what we talked about at the beginning of the problem, isn't that exactly what happened? Okay. I've got that sine graph, but it only takes half as many radians as it did before he repeats. Okay. Now, a lot of times on these graphs, you're going to be asked to go ahead and sketch a minimum 2 periods. Well, this is always going to give you 1 full period. Well, how can I get a second one? Yeah, just repeat the pattern you see. So after this 0 would be another max, then a 0, then a min, then a 0. There you go. And it would just repeat over and over again. This is sine of 2x. Okay. Okay. Now, I know that seems a little strange. Okay. Probably even unnecessary. Is there anybody out there thinking, you know what, I didn't need to do that in order to get the sketch? Probably a few people. Okay. But here's the thing. Here's why I'm really going to be stressing this particular strategy. Everybody would agree these transformations are pretty basic, right? They're pretty straightforward. Okay. Well, here's what our goal is. Here's the type of graph we want to get to. -3 cosine 2x minus pi over 2 plus 4. See, our goal is to go ahead and be able to sketch reasonably well much more complicated graphs like that. Okay, so this method right here that I'm talking about, it will absolutely be useful to you when you get there because it keeps everything organized for you. Okay, so there is a purpose behind this. Okay, so let's try it again. Let's try one more. Cosine of 1/2 x. Okay, so let's go ahead and start with just cosine first. Cosine starts with a what? Okay, max. And then it goes to a 0, minimum, 0, and then a maximum. So again, we have that curvy V. And so you'll notice I did go 2 pi. The original graph always has a period of 2 pi radians. So I have enough room. I'm going to go ahead and draw this again. Okay. Just repeat the dots one more time. There you go. Now look at this grid. It's different than the previous one. This one goes all the way out to 4 pi. Why would they change the grid? What's going to happen here? It's going to stretch. Wait a minute. I see 1/2 x. Remember, what's that key word? Whatever you multiply x by, the reciprocal is the true scale factor. So the reciprocal of 1/2 is 2. So I can expect this graph to take twice as many radians in order to repeat itself. Okay. Well, let's use that strategy we did a moment ago. I'm going to create a compound inequality between 0 and 2 pi. Whether it's sine or cosine, you always start out the same way because both of them have a period of 2 pi. What am I going to put in the middle? There you go. Whatever is in parentheses, any horizontal transformations, it's going right in the middle of this. So I'm going to go ahead and say, 1/2 x or x over 2. So what I want to go ahead and do now is simplify, get the x isolated in the middle. Well, how would I do that? Okay, so I just multiply through by 2, right? So that's going to give me the 1x in the middle. 0 times 2 is still 0. 2 times 2 pi? 4 pi. So this right here is telling you what one period of the new graph is going to be. So we're right. It's got to stretch itself all the way to 4 pi radians. Okay. Now, what's happening vertically? Is there anything outside the parentheses? No. So if there's nothing outside the parentheses, that means that those 5 key values of y, they're not changing. Remember, cosine started with a 1, then had a 0, its minimum, a 0, and a maximum. Okay. Once I've simplified my compound inequality, this is where I'm going to pair them up. What am I going to pair this first 0 with? There you go. So I'm going to pair that lower boundary with the first y value. What am I going to pair the 4 pi with? Okay. the last one. So I'm always going to pair the upper boundary with the last y value. So right there, I've already given myself 2 points. I know that on the graph of cosine of 1/2 x, I got to have the ordered pair 0, 1, and I've got to have the ordered pair 4 pi, 1. Now I have the y values for 3 other ordered pairs, but how do I find those x's? What did I do a moment ago? Now, before you divide by 4, you always want to take the upper and subtract the lower. Now here it really doesn't matter, but you won't always have a lower boundary that's 0. Okay, so always subtract first. So 4 pi minus 0 is 4 pi, and you always divide that by 4. So what am I going to be adding over and over again? This time it's pi, so that's going to change by problem as well. It's not always going to be the same. Okay, so I'm going to start with 0 plus pi. Well, that'll give me pi. Plus pi, what's that? 2 pi. Plus pi, 3 pi. And should it always match up when you get to the end? Yeah. Okay, what's 3 pi plus pi? 4 pi. So there we go. So you've got 5 ordered pairs for one period of your transform graph. Okay. So we have 0, 1. Then what's the next ordered pair? Yeah, remember the top row is your x's, the bottom one's your y. So pi comma 0. So I'm going to go to pi and just put it right there on the axis. What's the next one? 2 pi negative 1. And we have 3 pi 0. And we finish up with 4 pi comma 1. There we go. Now when I connect them with a smooth curve, what did happen? Yeah, the graph was stretched twice what it originally was. Okay. Questions? Okay, anybody having a hard time? Am I not sure where I got anything from? Okay, so let's kind of wrap up the period here. Let me take this out of the way. It says, can you describe what happened to the graphs? We've already talked about the reciprocal and the horizontal dilation, so I'm not worried about that. Now, the periods for each of these two functions can be found by this. 2 pi over b. Now, b is always the coefficient of x. Okay, because one full cycle will be graphed on this interval. In general, we can say that for these two functions, the period is 2 pi over b. So if I were to go back to these graphs here, in this case, for sine of 2x, b would equal 2. For cosine of 1/2 x, b would be 1/2. So go ahead and apply the formula, and let's see if it's accurate. Okay, 2 pi divided by b, but for problem 4a, b was 2. Well, what's 2 pi divided by 2? Pi, and that was the period for that particular problem. If I'm going to apply it to this second one here, 2 pi over b, but b is 1/2. Okay. Well, what's 2 pi divided by 1/2? That is 4 pi. Again, the period that I got for that one. Okay. Now it says, compare and contrast what occurs to the period when b is greater than 1. Now, we know this is a horizontal dilation, but what I would like you to tell me, if the scale factor for b is greater than 1, this is a horizontal what? Is that a compression or expansion? It's a compression. So what happens if your scale factor b is between 0 and 1? That's when it's a horizontal expansion, or stretch if you want to call it. There we go. Okay. Anybody having a hard time? Boop. Okay. We should be able to get away with one more before we take off today. Phase shift for a trig function is a horizontal transformation of the graph's initial point. Now, we usually go ahead and say shift, we say translation, but it's just a name change when we're talking about trig functions. If we're going to go ahead and translate or shift it, we just call that a phase shift. Okay, so it's just a new vocabulary word. Let's take a look at this one. Y equals sine of x minus pi. Okay, let me get the pre-image first. Sine always starts with a what? 0. Then we have a maximum, 0, minimum, 0. Okay, so there's one period for sine. And I have enough room here. I'll definitely go ahead and draw a few more of these patterns. Okay, I think that's enough. And there we go. Okay, so this is the pre-image. This is just sine of x, the parent. Okay, so again, on this one, it's probably not necessary to go ahead and use that strategy. But I think it's really important that you understand how it works now so that it's very helpful when we get to those more complicated ones. All right, so what's happening here? Is it a horizontal or a vertical shift? Horizontal, okay, because it's directly affecting the x. But again, what's the thing we need to remember when we add or subtract to x? Oh, someone said it. It's the what? You got to take the opposite. Okay, so if I'm subtracting a value, that means I'm going to shift it to the right. If I were adding, that means I'm going to shift it to the left. You take the opposite direction. Okay, now it doesn't matter that in this case we are not multiplying at all. Whatever's in the parentheses, my horizontal transformation, I'm still going to create a compound inequality out of that. So I'm going to put 0 less than or equal to, in this case, x minus pi, less than or equal to 2 pi. You always start your compound inequality between 0 and 2 pi. Okay. Well, how would I isolate x? Yeah, just go ahead and add pi to all three parts. So a perfect example, this is our first one where the bottom boundary is no longer 0. Okay, so pi is less than or equal to x, which is less than or equal to what? 3 pi. So graphically, between pi and 3 pi, I should see one period of this graph. One repeating cycle. Okay, so now I'm going to go ahead and put this compound inequality to the side for just a second. Now I'm going to focus on my y values. Is there anything happening vertically? No, nothing outside the parentheses. So I'm going to use the same values for y. Remember, we started with a 0, then a maximum, 0, minimum, and then we get back to a 0. Okay. How do I start getting my ordered pairs? What do I do? Well, now, before we subtract and divide, we already know 2 of them. How? There you go. We're going to take the lower boundary, and we always pair it with the first y value. Okay. What am I going to do with the upper boundary? I'm always going to put it with the last y value. So I'm going to put 3 pi right here. Okay. So now, Noe, you said something about subtracting. What do you want me to do? There you go. So always subtract the lower from the upper. So what is 3 pi minus pi? 2 pi. Now that difference we always divide by what? 4. So what does this become? 1/2 pi, or pi over 2. See, it changes depending on what you're asked to graph. So starting with this first one right here, pi, all I want to do is add 2 pi. Add another 2 pi, or excuse me, pi over 2. Add pi over 2 until I finish filling out that first row. Okay, so take a few seconds to go ahead and do that. Let's see if we can all get the same values. Because I already know I have the first ordered pair here, pi comma 0. I have another ordered pair here at 3 pi 0. And you could do this algebraically, or you kind of just think about what we know on the unit circle. Remember, pi over 2 is just 1/4. So what's pi plus pi over 2? That would be 3 pi over 2. Everybody okay with where I got that value from? So now just keep adding pi over 2 again and again. So now what's 3 pi over 2 plus pi over 2? Okay, that would be 2 pi. Because it would be 4 pi over 2, right? Plus pi over 2. 5 pi over 2. Now remember, it should match up with your upper boundary. What's 5 pi over 2 plus pi over 2? 6 pi over 2, and that is 3 pi. Okay. So let's see here. I got pi 0. So see, that point is this one right here. It's just been shifted pi units to the right. Then I have 3 pi over 2, 1. That's just this point right here, shifted pi units to the right. And you're going to notice that just repeating that pattern over and over again. 2 pi is 0. 5 pi over 2, or 2.5 pi, is a negative 1. And then 3 pi gave me 0. So all I did was take the graph and I shifted it pi radians to the right. Now that's one cycle, one period. What if I want multiple? Yeah, just repeat the dot pattern you ended up with. So the next one I know would be max 0, and then we're off the grid. Now if I were to go backwards, I could say minimum 0, maximum 0. Okay. And I mean, you can continue as far as your graph would allow, but that's all we need right there. So I realize this strategy probably isn't very useful right now, but especially when we get to those more complicated ones, it's going to be very useful to you. Okay, so I really encourage you to go ahead and try this. Now, if you already have your own method, if you're able to transform it, you're good to go. That's all I'm looking for. Okay. All right. Well, here's what I'm going to do. I'm going to go ahead and give you your assignments. This is going to be due on Tuesday. All right. We'll wrap this up on Monday. We'll take our quiz. Maybe we'll have a little bit of time to go ahead and work on this in class. I can't guarantee that, but we'll see what happens. That gives you plenty of time to do this. Now, you'll notice I said I wasn't going to go ahead and copy assignments for you anymore. But on these next two, I decided to go ahead and do that because what are we doing in these two lessons? We're graphing them. So I'm going to go ahead and provide you guys the grids. I think that's just going to make it a lot easier. Okay. All right. All right, let's go ahead and get those calculators back up to the front. Thank you very much, guys.